I want to welcome everyone to the derivative trading tutorial for today. Yeah, are you sure you can't see that? You want to sit over here? Is that easier for you? Otherwise, you're going to be doing that all the time. Okay. So we haven't really got long to go. As you know, there will be one more lecture tomorrow, and then there will be one more. So next Thursday is the last time we will meet for the tutorial. So what I want to do today actually is to make a final connection between the various option Greeks and how you would tie them together. And I'm not really telling you anything or asking you to learn anything extra. It is actually just an extension of, good morning, an extension of what you have been learning from Xin-Ming, and you're going to see that in a moment. Yeah, you're going to see that in a moment, so as you know, I'm a great supporter of finance theory and how you can apply that to practice. And today I encourage you, whenever I show you some theory, I strongly encourage you to ask yourself, okay, how can I apply it in practice? And when I show you something in practice, I strongly encourage you to think, what is the theory behind that? Okay, I have tidied up the tutorial notes a little bit. I wasn't entirely happy with it, so you can download that today from Blackboard. It has the most up-to-date version, and I think these slides, I think I had too much stuff in there previously, and it was causing some confusion. So today, what I want to do is to go through the connection between delta and sigma. Sigma is implied volatility, and theta and gamma. I want to tie them all together and present to you how they are related and how you would try to manage an option portfolio in practice. So this is actually implied volatility. Okay, and I think between now, so next week, we will probably just do a review session in the tutorial. I will, answer your questions or maybe go through some of the lecture material and give you a summary. The final exam will be next Friday at 6:30 in the evening in YIA LT7, and it would be it would cover the entire course, but obviously the second half should have more weighting. Okay, there are questions that will come from the tutorial. They won't be trick questions. Okay? So if you have been listening to me in the tutorial, I think you'll be fine. I don't mean to give you a hard time. Xin-Ming asked me to make a contribution. He said, what have I been talking to you guys in the tutorial? Okay, so I told him, and I have added, he asked me to add a couple of questions in that regard. Okay, so here's the timetable. So today is already the 21st of February. So like I said, tomorrow we will meet for the presentations. And thank you for your submissions, by the way. So I'm going to tidy them up today and download them, make sure they are working. We meet one more time next week, and that's it. And if you actually, Lu Yang, you were saying, if you want to come on Saturday morning, especially for this week, to get a preview, that would be Saturday morning, 8:30, okay? because if you want to get an idea, you want to get an advanced preview of the last tutorial so that you don't have to wait until next Thursday. I can understand that. Okay, so do you think you guys would want to do that? I mean, I can still be here. I can still make myself available. Okay, but anyway, I'll leave that to you. Now, for today, I want to finally share with you the theoretical connection, not just theoretical, but practical as well, the practical connection between delta and gamma and sigma and theta. Okay, notice that these are all, so sigma is a little bit different. So delta is the price sensitivity. So let's stick with a call, or any derivative f can be a call, can be a put, can even be a forward. F is just something out there which is a derivative. So delta is the change. Thank you. Yeah. So delta is the change of the derivative price with regard to the underlying. Gamma is just the second derivative. I'm trying to be consistent with the notation that is used in the book by John Hull. Now, sigma is not actually any of these, which is why I kind of single it out. Okay. Sigma is not the same as vega. Vega is this one, okay? In fact, the funny thing is vega, as far as I know, vega is not actually a Greek alphabet. Sigma is. But anyway, so sigma is the implied volatility and theta is just the change in price with regard to time. So if you know even just a little bit about calculus, you will understand that when you are trying to figure out the change in price with respect to time, what you are saying is, I want to know this when nothing else changes, or what we always are so fond of saying, all else being equal. Okay, so that is the starting point. Now, I would invite you to have a look at, so the starting point is, if you go to Hull, if you go to the textbook at about page 354 in the current edition of the House, which is chapter 15, there is a formula here, formula 15.16. Now, like I said, I am not telling you anything new. This equation actually presents itself in the lecture notes. I'll show you in a moment. Okay. Now, I'm not going to derive it, but actually the derivation is rather simple. But what this formula is saying, if I ask you to explain this formula in English, you see, mathematics actually is a language. In a way, you can look at it like that. But if I was to ask you to explain formula 15.16 in plain English, what would you actually say to that? Or is it just a load of symbols? Or are you just going to read to me, oh, df by dt plus rs dm by ds? How would you explain that to me? You can have a go. If ever you go for not even a quant interview, but something which is slightly more technical, like a derivative sales, I think this is a reasonable thing to ask. You know why? Because I bet you, out of 10 candidates, 7 of them cannot answer. Do you want to be in the 7 or do you want to be in the other 3? Now, anyway, so let me write that down here. Okay, I'm going to give you all these notes, which I always do, as you know. So what was it? So df, so f is just the price of a derivative, any derivative. Now, if you want to derive this formula, feel free. I'm not going to do that this morning, but it's all there in the book, so I don't add any value. But I'm just going to take that. The derivation is not hard because you just start from here. And I think Professor Gao Zhenyu, he probably will do it with you. Okay, but I'm more interested in the actual final result, which is 15.16, and 15.16 says something like this. What was it again? Now this is, by the way, this is 15.16 represented, okay? But they are quite confusing with the notation, and I'll show you why in a moment. But don't worry about that for now, okay? So when you look at it, it's RF df dt plus RS df ds plus a half. Hold on a second. Sorry, RS. Yeah. Plus a half sigma square S square d2f ds square is equal to RF. Now don't worry when you see this, and you'll find that by the end of this tutorial, you practically don't have to remember it because you're going to understand it so well. So my job for today is to reduce this complexity or apparent complexity into something that is very simple for you. Okay. First of all, df dt, if you want to use a Greek letter, that is actually theta. Okay. Plus, now R is the interest rate, df ds is just the delta, plus a half sigma square S square. Now what's d2f ds square? This is just gamma. So I am simply replacing this formula with all the respective Greeks, except for sigma. Okay. Now I'll tell you what this is saying. This is really just saying that if you have a derivative, any kind of derivative, and if you were to multiply it by the risk-free rate or the borrowing rate, interest rate, whatever you want to call it, you multiply by the current borrowing rate, it should be equal to all these things on the left-hand side. What are they? First of all, there's a time decay. If you want to put it in English, okay, the theta is the time decay. It's the time decay plus the interest rate. Now you know all of these things. There's nothing here that you don't know, okay? It should be equal to time decay plus the product of interest rate and the underlying stock price itself times the delta plus a half is a half, times the implied volatility times the square of the implied volatility and the square of the price and the square of, sorry, not the square, the gamma, okay, times gamma. Now, this is kind of like making a Caesar salad or a spaghetti bolognese, isn't it? So if I ask you, how do you make spaghetti bolognese? You have some meat, minced meat, you have spaghetti, you have a sauce, you have some olive oil, you add some cheese. This is kind of the same thing. Okay. So we are saying that, now, like I said, I don't want to prove it. For me, it's not about proving, it's about using the result. So this formula is in fact the formula, it is the same formula that was presented to you in lecture 6 on page 21, except that it is quite confusing. The notation that they are using there is pi. So I don't blame students for getting confused, but when you study this carefully, this is exactly the same formula. So there's theta here, there is r and s and delta plus a half sigma square s square. This is theta, gamma, but this is the capital form. So capital gamma is like this. The lowercase gamma is like this, but it's gamma, okay? So this formula on page 21 is of lecture 6 is the same as the formula that was initially presented in the book by John Howe on page 354 under the derivations of the Black-Scholes formula. This is kind of the result. So I'm starting at the end and I'm stating the result to you. Yes.
With the Black-Scholes model, I think Black-Scholes model is both option. But if for future, can we still use this kind of?
Okay, so let me, if you don't mind, let me just correct your question slightly.
Okay.
You are deriving this, I think, not from, but for the Black-Scholes model. For the Black-Scholes model. Now, the Black-Scholes, which is based on if you look at this, the short answer is yes, okay? Because if you are really interested, Jackie, we can do this later on, but the derivation of the Black-Scholes equation, not from, for, is based on a simple observation in stochastic calculus called the Ito's lemma, which simply says that if something, okay, don't look at this. Okay, now what is Ito's lemma? Because you asked that question, I'm happy to share with you. Ito's lemma simply says that if there is a random process, okay, now it sounds very simple when you say it, but it took a great mathematician actually to discover that. When there is a random process, like a stock price, okay, and then there is a derivative, okay. The derivative can be a call, can be a put, can be a future, can be a forward, anything. Okay. So when there's a derivative x, and so when there's a random process x, and there's a derivative y, okay, doesn't matter what kind of derivative. Okay. If x follows a random process, any derivative of that random process is also a random process. That's Ito's lemma. Okay, now it may seem obvious to you. Do you know what I'm saying? At least you, Jackie, even if you don't understand the details, you understand the English that I'm saying to you. If there is something that follows a random process, any derivative of that, a call price, a put price, a forward price, a futures price, also will be a random process. And from that, it is actually from that, not from any Black-Scholes or this or that. It is from that simple observation that you can derive the relationship like this. Okay, that is why it works. That is why it is not exclusive to options. That's your question, right? Yeah. Okay. So when I say that f is any kind of derivative, I am trying to make that, a more generic argument. Okay, thank you for that question. But anyway, now, and I hope you will really understand, because this is really good for you. Okay, and very useful. Now you're okay with that, right? So let me do a bit of rearrangement. Now, I'm going to just take this formula and I'm going to write it the other way around. I'm going to put RF minus R delta S. Now I haven't changed anything, by the way, is equal to theta plus a half sigma square S square times gamma. Is everyone okay with that? I haven't done anything. What I did was I took RS delta to the other side and I tidied it up and I switched the sequence. So these two formulas are the same, but I have rearranged it. Can you see that? Yeah. Now I can actually go one step further. This is not hard, guys. This is baby algebra. So R F minus delta S now it's in a much more user-friendly format. Now I'll tell you what's coming up. Is everyone okay with that up to now? Yeah? Not really that tricky. If you remember this, surely you can do this, which will get you to number 3. Okay. Now I think you can see what's coming up. And we have said that now let me give it the sort of English interpretation here. Okay, now the English interpretation of this, once you understand the actual interpretation, you don't even have to remember it. I'll tell you what the interpretation is. Okay, the interpretation is this. So for any option, the time decay plus a half times the implied vol times the square of the price times gamma, that should be equal to interest rate multiplied by the derivative price minus delta S. Now I'm just, again, I'm trying to speak English and translate a formula from mathematics into English. Okay? What does this actually mean? That is the question. Okay? First of all, what does the left-hand side mean? And what does the right-hand side mean? And I'm going to explain to you now what these things are. Okay? Now, you have to, and then we, as you remember, so think of last week, what we talked about last week, when we had an option payoff. As you remember, the option payoff is non-linear. So hard to draw these things. And so what I was saying, what I was saying to you was that if you are long a call, let's say you are long a call and you actually delta hedge it with some stocks, delta times the price, then when the market goes up, your option is going to make more money, so more profit. How can I put it? So when the market goes up, you make more money from your call than the money that you are losing from your hedge, because your hedge is linear. But when the market is falling, you are losing money on your call, but you are making money on the hedge. You make more money from your hedge than your call. So when the market is going up, so this is your call option, and this is your delta hedge. So your call option is always making more money than what you are losing on the hedge. When the market is falling, you are losing money on your call, but you are always losing less than what you are making in your hedge. You understand that, because that really goes to the heart of option trading. You understand that. I think it's I wouldn't say it's better than understanding all the formulas, but it would help you, navigate a lot of the trading ideas that traders are thinking about. Are you okay with that? Yeah, that's right. And that is because you actually get paid this part, which, as I said to you, is known as gamma revenue. Gamma revenue. And when the market is falling, you are likewise making gamma revenue. Now, this really sounds too good to be true. You are making money as market's going up. You practically you don't have to think. You just put on this position and you go home and you just go to bed, and it'll make money by itself. It sounds too good to be true. And it is too good to be true, because don't forget that an option is actually losing value day by day if nothing happens. It's like a balloon which will lose air from one day to the next. Okay, so what is actually going on? I'll tell you what is going on. What is going on is you are actually paying for the gamma revenue. How much are you paying? You are paying theta. That's what you are paying. So the time decay should be the same, should be equal to gamma revenue. Now this is the gamma revenue times sigma square s square, times a half sigma square s square times gamma. This is known as the gamma revenue. This is the gamma revenue. Now this is an important point, so please remember, this is the gamma revenue that is predicted by the market. Why do I say predicted? Because, exactly, very good, Jackie. Because of the implied volatility. Now this implied volatility can change from one day to the next. So when people talk about the market price of risk, I guess that's what it is. The volatility right now, it could be 16, it could be 17 and a half. Why isn't it 35? Because the market doesn't believe it should be 35, but it can be when things change. Suddenly two countries go to war. It can go up to 75. It did at one stage during the 2008 financial crisis, for example. This is the gamma revenue, and this is the time decay. Now, by the way, this theta value, df by dt, I ask you, this quantity, df by dt, is it positive or is it negative? It is always a negative number. Okay, at least for plain vanilla derivatives. There are some circumstances, there are some derivatives where an option can increase in value when the time becomes shorter and shorter. But that's a special category. Most of the time, the theta is a negative. So that is why if you just go to our old friend, you know who our old friend is, optionprice.com. When you go there, and you price any kind of option, you see that the theta value is minus 0.054 for a call or minus 0.041 for a put. Never mind call or put is negative. Okay? So you can already see, if I just go back a bit, so look, if you look at the right hand side, although you are adding theta to it, theta itself is going to be a negative number, I can promise you that. So what is that now saying? It is saying that if sigma can perfectly predict the market movements, then the gamma revenue that you earn would be offset by the theta. Okay. Now, what is the left-hand side? The left-hand side actually is a lot easier than you think. What actually is the left-hand side? I'll give you a clue. This is the risk-free rate to start with, or the borrowing rate. Okay, let me help you out. F is a derivative. Any derivative. Let's just say a call option. Okay, so you're long a call and you are short some stocks. So this thing in brackets is actually the cost of your portfolio. If you multiply that by the risk-free rate, it is actually the funding cost, or the return that you're going to earn on your, is the risk-free return you are going to earn on that delta neutral portfolio. Okay, so what we are saying here is, in a perfect world, okay, let me say this in English. In a perfect world where sigma can predict future market movements, the sum of theta, which is a negative value, and gamma revenue should be equal to the risk-free funding cost of your delta neutral portfolio. Is that quite clear? That might be the most important thing I've said all time. Let me say it again. So in a world where the implied volatility, or the sigma, can predict price movements, then the sum total of theta, which works against you, okay, if you are long an option, the sum total of theta, of time decay, plus the gamma revenue that you can earn, when you add the two together, your net gain should simply be equal to the cost of carry of your delta neutral portfolio. Would you like me to make a slide and just, maybe that's a good idea. I'm going to just make a slide, or maybe I already have done a little later. I kind of have, but in summary, 3. Okay, you can look at these slides later when you go home. So in a perfect world where sigma, i.e. the implied volatility, can perfectly predict market price movement, or I should say dispersion is probably a more appropriate word. You'll see why in a moment. I'm going to take you back to that binomial thing. In a perfect world where sigma can perfectly predict market price movements or market price dispersions, then the sum of theta, i.e. time decay, and gamma revenue should equal to the funding cost or the one period portfolio return, get the funding cost of a delta neutral portfolio. Now, if you, I don't ask you to remember, if you understand this statement, you understand a lot about option pricing and option trading. Is everyone okay with that? Now, I'll tell you why. Because this is the portfolio. Yeah, this is the portfolio. If you have something like this, you have that portfolio. You have a call, and then you are short some stocks. You can see that, right? So you already have that portfolio here. Okay. Correct. In fact, I want to show you, you are right what you just said, okay? I want to show you a special case when interest rates, not delta, when interest rate is zero. Let's imagine when interest rates are zero. Now, when interest rates are zero, what does it mean? You get something pretty interesting, because if interest rates are zero, then you're going to get this. Gamma, exactly. Gamma revenue is equal to time decay. Okay, and even when interest rates are not zero, it doesn't really get that much more complicated, because you simply, the difference here is zero, but the difference here is just the funding rate on that portfolio using the risk-free rate. But let me prove to you that this is true. Now, if you go to our old friend again, and I'm going to put interest rate zero, I'm going to put dividend yield as zero as well, and let me just put that as 90 days. You get some more interesting numbers when you do that. So you are now pricing an at-the-money option. And let me use, I'm going to use 25, I'm going to use 32. You'll see why in a moment I'm using 32. So now I am pricing a 90-day at-the-money option where the strike is 100 and the stock price is also 100 and volatility is 32. Now, let me just write down some of the numbers on the right-hand side. So gamma is 0.025. Actually, you know, it's not really precise enough. So here the option price is 6.333 and the gamma is 0.025. Now let me open up another pricer and I want to try and show you. So 90 days. Now this one is just another, but this one is Excel base. Can you see the value of the option? It's actually 6.33, not 333, but 3325. And the gamma is 0.02502. So there are actually a whole load of decimal, a whole load of digits following it. And I just want to show you this calculator is not bullshit, because the call option is worth 6.333. Delta is 0.532, and it is, but my calculator is more precise. So here the gamma is 0.025, but it's actually 0.025027, and the theta is minus 0.035. Now, here is where we have a bit of a problem, and please listen carefully. Can you see that there's a calendar theta here? Calendar theta point. Now, first of all, this calendar theta value is the theta value that is being shown here. Unfortunately, with a lot of these prices that you get on the street, they just show you the calendar theta, and you cannot use calendar theta for a lot of these mathematical computations. You need to use what I call a trading day theta. Okay, now I'll tell you what that is. So first of all, this is a calendar theta, okay, minus 0.035. What is a calendar theta? The relationship between a calendar theta is, so let's say this is a calendar theta. You multiply that by 365, you get the annual theta. And if you divide the annual theta by 256, you get what we call the trading day theta. Now, the trading day theta is actually what you will lose. So I don't know why they keep these prices, they keep quoting the calendar theta. If you don't believe me, so here, if the calendar theta is 0.051, I'm just going to forget the minus sign. You multiply that by 356, and you divide it by 365, and then you divide by 256. What do you get? You should get 0.05005. Do you get that? Try it. So 3511 times 365 divided by 256 is 0.05005. Okay, calendar theta is practically useless. Now, what is this value? What is its value? 0.05005. This is what you will lose from one day to the next. In your option price, yes. Okay. If you change that to 89, can you see that the price has changed? The value of the option has changed. Okay, that is the time decay. Okay. Now, another thing I want to do is, now I want to show you what is the gamma revenue. Now, I already told you that gamma revenue, or the market predicted gamma revenue, is a half sigma. You can actually do this. Okay, sigma s all squared is the same. Okay, now that is equal to a half times, what is sigma? Sigma. Sigma is 32, but I need to have a daily sigma, which is 32 divided by the square root of trading days. So it's actually, this is 16. That is why I choose 32. Times 100 squared multiplied by gamma, 0.025027. Now, I'm not really doing anything which is rocket science, but when you do this, you get exactly. Okay, so this is so 32% divided by 16 is actually is 2% or 0.002. Multiplied by 0.025027. What? 32 divided by 6, this is 32%, I'm sorry, 32%. Okay, now, so that is, in fact, I don't even need a calculator. This is just 2. It's 2. So it is the square of 2. What is the square of 2? Okay. No, you don't need to. The only reason I need to do this conversion here is that you do not use calendar theta for any of this work that you do. You always have to use the trading day theta. Actually, they mentioned that in the whole book. Okay. Now, if you do that, so the square of 2 is 4. 4 divided by 2 is 2. So it's 2 times 0.025027. Can someone tell me what that is equal to? I'm going to give you guys some 2 points. There are only 6 people here. You just say something, you get one of these. Okay. Huh? What is it?
0.050054.
Okay. Except for the rounding error, if you forgive me for getting something in the 6th decimal place, isn't this the same as that? What is that? That is the trading day theta. Now, this is not a coincidence. Let's try another example. I don't mind to do anything. You give me an example. What do you want to price? Tell me what you want to price.
I have a question on the implied volatility. Yeah. Here, the volatility is what you input in the model.
Yeah.
But the implied volatility is something that you obtain from the market price.
Yeah. So this is the implied volatility. I am taking this input from the market. Yeah. So although it just says, well, I can say implied vol, it doesn't matter. Okay. This is the implied vol. This is the vol I would have been able to back out from the option price, for example. Now let's try and price something else. So yeah, maybe you can give me a spot price first. What spot price would you like to use? This is like David Copperfield. You know David Copperfield, right? The magician, the magic guy. So he picks a member of the audience and he will say, "Do I know you? I don't know you, right? So let's do some magic." Okay, you tell me what spot price you like to use. 200. Okay. So Jackie, what strike? Try not to be too far away from 200. 190. Okay. Implied vol. Yeah, and what would you like to use? Try and if you can pick something which is a multiple of 8, it's going to help. 16, right? If you want to use 20, 48, yeah, 48 is okay. 48 is okay, or even 40. Whoops. Okay, we use 48. And let's just leave it at 90 days, okay? Now, so we got a few things to work on. Let me just rub that off. So I'm going to give you another example. By the way, I want to re-emphasize that even when interest rates are not zero, this still works, but it just makes it a lot simpler. When interest rates are zero, then the term on the left-hand side actually disappears. But even if it's still there, this isn't really that hard. You just take the option price, and then you take away the value of S times delta, and then you just have to do one more calculation. But if R is zero, then it's easier to calculate. But even if R was not zero, this identity is absolutely rock solid. Okay, now let me just rub off all this. I can't get rid of it. Okay, so first of all, the calendar day theta is 0.09991. So the calendar day theta is minus 0.09991. So the trading day theta should be simply this one times 365 divided by 256. What is that? So 0.09991 times 365 divided by 256, 0.14244.
Yes.
So for every trading day, you are going to lose around 14 cents. That is the trading day theta. Now, remember, as I said, the trading day theta is what you work with in option pricing. And now I'm going to try and work out the implied gamma revenue, which is a half times sigma s all squared times gamma. Now I'm just going to plug them in like making a spaghetti bolognese. So this is equal to a half times sigma is now 48%, so it is 0.48 divided by the square root of 256 times 200 is the square of that, multiplied by S is the stock price, or the spot price, I should say. Yeah, so because you guys said 200, so I'm now using 200. Multiplied by gamma, which is, you can read that off, is 0.007914. Now I'm going to multiply all this stuff. So first of all, I'm going to do the easy bit, which is 0.48 divided by 16. I can't rub this off. Why is it so cool? The eraser. Okay, here we go. So that is a half times what is that? 0.03 times 200. Are you guys still with me? Square of that multiplied by 0.007914. Now that is equal to a half times, what is 3 times 200? That is 6. The square of 6 is going to be 36. So 36 divided by 2 is 18. gamma, that you mean that 0.007914 thing, that came from here. The gamma is given. Now, in fact, if you were to price this thing, online, which I'm happy to do, you would oh, have I got the right thing? So 248 gamma 0.00, yeah, you see they rounded it to 0.008. So gamma is simply the second derivative. Is the differentiating delta with respect to price. So that one you can calculate quite easily. The 0.008 here is in fact 0.007914. So again, immediately you see that if I was to use our old friend, you run into problems because it's not precise enough. But now it is. And I said that the trading day theta is minus 0.14244. Now, what is this one here? Okay, so there's a little bit of rounding error. Okay, but if you just take the first 4 decimal places, they are the same. So this really works. And again, before you get completely buried and you lose your direction in all these formulas and in all these numbers and in all these Greeks and in all this computation, let me bring you back and say to you, what are we actually doing? What we are doing is we have demonstrated that this formula here at the top, which is just a rearrangement of this formula here, formula number 1, which was given to you on page 21 of lecture 6, is the same formula. I just don't like their notation. This pi here is going to confuse people. Okay, and this formula itself, you can go to How, page 354. You get the same formula. But like I said, if you truly are interested in the derivation, you do need to understand a little bit about Ito's lemma and stochastic calculus, a stochastic differential equation, which isn't really that hard, but that's not what I want to do today. Okay, so it all ties together. In the end, although you start very kind of a little bit complicated, but the result is extremely elegant. The result is that when you have a portfolio where you have maybe you have an option, call option, and then you are running some position on that, then the funding rate of that, okay, the funding rate of that would be the sum of the time decay and the gamma revenue. Or if you put it the other way around, okay, if you're running this kind of portfolio, then the difference between the time decay, because time decay is a negative parameter, the difference between your time decay that you lose and the gamma revenue that you earn, the net difference of these two should simply be the risk-free return you can earn on your delta neutral portfolio. And if the risk-free rate happens to be 0, then ultimately you can say that minus theta is a half sigma s squared gamma. Okay, if you can follow me up to now and you are able to repeat what I just said, you know a lot about option pricing. In the end, ladies and gentlemen, and I raised this question last week. I asked you, when you are paying for an option, like our old friend, our old friend optionprice.com. So you have an option here. The underlying price is 200. The exercise price 190. Is a 3-month option. You are taking out $24 from your pocket to pay for it. What are you paying? Well, apart from $10 of intrinsic value, which you can see, is the strike. Apart from that, the other $13 or $14, what you are paying for, actually, you are paying for the theta of day after day after day. You add them up, and it's really just an integrated, you are paying for this in the end, okay? So it's the integration of all the individual little theta. That's what you are paying for. Okay, the theta is, you are paying for the sort of cumulative daily gamma revenue. So you add that up over 90 days, and the gamma revenue that you earn should be exactly equal to the time value that you would lose. Which is another way of saying, in a perfect world, when you run a delta neutral portfolio, you don't make money, you don't lose money, which is what finance is all about. Right? There's no free lunch. And I find this, everything ties together, and it is very, very elegant. Now, please think back and recall a lot earlier when we started talking about the binomial. This is not something different. This is the insights from binomial, is where all that other stuff came from. Because in the binomial model, we are saying that, you still remember that, right? So the dispersion parameter is the only thing I need to specify. So let's say 10% dispersion. So the price only goes to either 22 or 18. This is another way of stating your volatility. Okay. And then, the approach here was that if this was true, then you can prove that if you have a certain delta hedge, then you can make your portfolio entirely risk-free, in that, regardless of what happens, your portfolio value will have the same outcome. So if that was the case, you should only earn the risk-free rate on that portfolio. The assumption here is that my dispersion is correct. If, and only if, my dispersion assumption is correct, which is to say it only goes to 22, it only goes down to 18. If that is correct, then this option is correctly priced. It's exactly the same as saying, if my implied vol is correct, and you would never know, but finance is all about assuming something before it happens. If your implied vol is correct, then you're going to earn some gamma revenue, but you're going to lose some time decay, and the difference between the two would just about cover your financing cost for your portfolio. And if your financing cost happens to be zero, which is a special case, and we've been looking at that just now with two examples of how the time decay is related to the gamma revenue. And I think I said all that. It's a long-winded way of saying what we are saying here. In a perfect, I come back to this, okay? So in a perfect world, I still don't like this formula, but this is the best we have. This is a Hull notation. So here pi is the price of a derivative. So in a perfect world where the implied volatility can perfectly predict market price movement, the sum of theta and gamma revenue, or I could say here, I could say the difference, because theta is a negative value, the difference of theta and gamma revenue should equal to the funding cost of a delta neutral portfolio. Do you understand this statement? This really goes to the heart of option pricing. Yes, we are. Yeah. Yeah, I guess you do, strictly speaking. Yeah. I'm going to have that. Okay, I'm not going to have it in cap. Just okay. The keywords here are the sum and the funding cost. Make sure you understand this, because you can carry that around for the rest of your life. And it will. Yes, yes. Come again.
So, how can I ensure the difference between F and delta times S is always positive?
How can I ensure that the difference between F
It's negative. I think it's gamma revenue should negative as well.
Mm-hmm.
Or no?
Gamma revenue always positive.
It's the first.
No, it's negative. Gamma revenue.
to now?
Yeah.
Yeah. So let me just show you. I haven't gone through the slides all this time, because I find that sometimes to be a bit of a distraction for you guys. But we're near the end, so I will show you just as a summary. So the relationship, so-called, between gamma revenue and the implied vol. So the gamma revenue is what the gamma revenue that we expect to earn is actually equal to the theta of the option when interest rates are zero. Okay, you get what you paid for, in other words. And if an option is valued fairly, which is to say the expected gamma revenue really is what you get over time, then the gamma revenue would be half times gamma times what I call 1 sigma of price movement. Now, what is 1 sigma of price movement? This is no different from saying it's a half times gamma times 1 sigma of price movement, and then the square of that. That's all that is. It's just translating that formula into English. Okay. Now, so here is the, but this one here. Now, this, again, by the way, this is the notation from Hull when he's using this delta pi, but here, the pi here, he's using that to represent a portfolio of an option and a stock. This is, if you don't believe me, you go to his book, and if you were to go to pages, well, this is the right page. So page 354, if you look at formula equation 15.13, I'm just repeating what he has there. This is the notation that he used, so it is quite confusing. But if you change this to P, then you don't have that confusion. So this pi, this r pi, this pi here is for a derivative. Okay, so that's why I say here P, capital P, is the delta neutral portfolio of the value of the option plus some stocks. Okay, and and then I go on to say that the sigma actually predicts the likely gamma revenue that you can earn, because it is really making a prediction on the likely price dispersion. And if that prediction is correct, the delta neutral portfolio will earn the risk-free rate of return. And if the risk-free rate is 0, which is actually a special case, okay, not the gamma revenue is not 0, but the gamma revenue plus the theta. Okay, so the risk-free rate, gamma revenue theta plus gamma revenue should be 0 too. Now, what does that mean? I'll tell you what that means. It means what we have been talking about for the last half hour. It means this. Okay, so this is in summary, slide 3. So if that was really true, then in a perfect world, when the implied volatility can perfectly predict the market dispersion, then when you add up your theta, which is a negative value, and the gamma revenue, which is always a positive value, it should equal to the funding cost of a delta neutral portfolio. Okay. All right. So if you can follow me up to now, I guess you can summarize everything in just one short paragraph like this, but it is also possible for you to write, a couple of pages explaining what I've just spent the last hour explaining to you. Okay. Okay. Is everyone okay with that? So what we have done today is, so apart from a bit of housekeeping, and I told you what will happen this week and next week in the tutorial, and also what is happening tomorrow. So Xinming will not be doing any more teaching. So we have the presentations tomorrow, and then in the last tutorial next week. So I will just give you a summary of the course, and also to run through what we will what might come up in the exam. And again, I think it probably is a good idea if you want to come to the Saturday morning session. Do you all want to do that? You guys were a little late, but I was saying to Xichang that I want to tell you too, okay? So, because you guys were a little bit late. So as you can see, what I have, if you look at the calendar carefully, there should be, the next tutorial cycle is this coming Saturday, and also next week on Thursday, but you have your exam actually on Friday. So it might actually be a good idea for you to come to the Saturday tutorial and just get everything over and done with. If you want to do that, I think it's a better idea for you. I can still make myself available next Thursday if you want. but feel free to come to the tutorial on Saturday morning. Okay? You mean a video? I can do that, yeah. In fact, this morning it's all recorded, and I will produce this as well. In fact, I think to be honest with you, I know that most people came last Saturday, but I think my coverage this morning is actually a bit better than last Saturday because I'm doing it a second time. It's like people playing in a rock concert. Okay? The last performance. Really?
Yeah.
All right. Yeah. Okay. So I'm going to let you go, and thank you for coming. And hopefully I'll see you tomorrow, and maybe I'll see you on Saturday morning. Okay. So you don't have to come next Thursday. I see that no one is coming. Okay.